it's up to you. But I think we are a little bit delayed on the schedule, so maybe I will ask the next speaker to present himself, which is, thank you so much, Filomena. Yes, our next speaker is José António Pereira from the Faculty of Dental Medicine of the University of Porto. José António has already a PhD in his medical area, and now he is my PhD student who already finished the thesis on mathematical modeling and applications, and he is together with me at the Universidade Aberta, or Open University, and in our Research Center of Statistics and Applications of the University of Lisbon here in Portugal. So the talk of José António focus on a very special new area that he was developing on statistical symmetry versus fuzzy approach. Please share your screen, José António, and present yourself.
Thank you very much, Oliveira, for your invitation. This is a great pleasure that I'm here with you to deliver a presentation.
Thank you. Thank you.
I hope you enjoy it. Thank you very much. So I'm going to share the screen. It's visible now?
Yes.
Okay. So let's start. My field of research is related with missing data by design, based on symmetry, because symmetry itself carries a lot of information that you can use to model some values, since symmetry can be quantified or proven. So to start with the definition of perfect symmetry is a variant under certain transformations, and in this case, our transformation, our type of symmetry that you're going to work with is the reflective symmetry. Is a rotation around one axis that is the axis of symmetry. So our field is also oral health, namely periodontology, and you want to grab information on the symmetry of the mouth, mostly in periodontal lesions, probably pocket depth, as you will see next. So the advantage of symmetry is use that information in control imputation. Also to diagnose when there is marked asymmetry, we can infer that there are other disease factors, unilateral disease factors that are causing that kind of problems. To understand the disease progression symmetry and help us to identify potential sites and targets. So we performed two approaches. One was statistical methods that we call advanced methods, and we comparing kernel density plots and the fuzzy approach. The data that we use the data from the National Health Center for Health Statistics from the United States, the very famous INANUS study, our computational resources, and our statistical methods. The advanced methods use gameless models, and you use a not very common approach to detect symmetry this way. As far as I know, it's the first time that this happens. I never saw work like that before. So you use to quantify the effect size of site, variable site, and this statistical significance, how it impacts the distribution parameters. After that, use likelihood ratio test to compare the two models, the null model and the side model. And at last, use fivefold cross-validation to measure the errors in the predictions. The RMSE, root mean square error, and the mean absolute error. The kernel density plots is a visual approach that you will see that is very clear, very straightforward. You can easily spot this difference that those other methods, statistical methods, cannot show it so clearly, as you'll see. We also perform the fuzzy approach. The fuzzy approach, we develop SM symmetry measure function to this case to quantify the symmetry between the two sides. I mean that there are contralateral sides, they are symmetrical sides in the math. Okay, so the gammas are very good model methods that you can model any distribution up to 4 parameters. You model the mu, the sigma, the scale, and the shape is the nu and tau. Okay. This is a parametric submodel that we are going to use that. Remember that when in our models, when sigma I appears, it means that you have considered the exponentialization of that values. Okay, it's the same with the nu. Okay, you're going to model all the parameters of the distribution with gammaless models with side variable as predictor. We compare both models. The null model with the alternative model is a side model. And you compare, after all, we'll compare both models with the likelihood ratio test, LRT. This is the way that's computed. We perform the 5 evaluation in the fivefold cross-validation, those metrics to how well the model performs or which model is better than the other. And if one model is better than the other, the concurrent model, we see that the side effect have effect. The side of the mouth has effect. It means that probability distribution of PPD, probability pocket depth, is affected by the location of the site that we are measuring. Okay, so this is the gammaless model fitted with the LRT test. As you can see, there is the side effect. The side, there's no effect on the mu, the central parameter, the location parameter, sorry. And the same happens with the sigma and the nu. We are working with X-Gauss distribution. X-Gauss distribution is an exponential modified Gauss distribution. It's defined by 3 parameters. One for location, one for scale, and the last one, the mu, for shape, the symmetry or asymmetry, if you can consider. So you see that those models for ISA values are very, very, very similar. And there is no difference between both models. When we approach the comparison with the fivefold cross-validations, we see that the RMS is not statistically significant between both models. It means that they commit the same kind of RMS error. And as you can see from the confidence interval at 90%, it means that there is no significance. The opposite happens with the MAE. This is that we find some statistical significance, although very, very, very small difference, as you can see. of course those numbers mean are rounded to the centesimal place. That's the other side that I propose to approach is the lingual side of the tooth, of both tooth. The 21 mean that are from the left side, and the opposite, the right side is 11. Okay, this is a reference value, the left side. As you can see, also we have no differences. And on the other hand, when you use cross-validation metrics, we see that there are statistical significant difference between both. So, as far as you can see, there is some difficulties to understand what means exactly each one of these tests. It means that it's very difficult to conclude about the symmetry or not between those two distributions. Well, there are some factors you can consider. Also the magnitude of the effect, the beta coefficient. In that case, there will be an arbitrary decision on what is large or small or neglectable, and the other values for RMSA and so on. They are very small differences. So, well, we are dealing in this case with the probability of being symmetric or not, and the tolerance between those points that you can call a sort of fuzziness is all the values inside the confidence interval. As you can see, this site is the DV is the first one, and there's no major difference between both distributions. As you can see, the right side is the red line, and the left side the blue line. As you can see, there is almost a perfect overlapping. There is a small difference in the peaks. On two. This is probability mass functions. We could also present some histograms, but I think that is, for me, in my opinion, is easily to spot the difference with those kind of graphs. Kernel density plots for probability mass functions. As you can see, there are the second one is the different. As you can see, you can spot some difference. They hardly overlap. Okay, the same with the mesolingual sides. So the fuzzy symmetry approach developed by Adelhard and Kohler, 1991. He decided because in nature, there is no. The perfect symmetry is very rare. So you know that our own face is symmetrical, but of course it's not perfectly symmetric. But if you notice that a face of a person have the eyes, the right places, and the nose, and so on, you can conclude that it's symmetrical. Okay, not perfectly symmetrical, it's symmetric. This called for a need of graduating, scoring the symmetry. So this Kohler decided to develop that idea based on the fuzzy sets theory. And create a membership function is a quantification of the symmetry or the grading of the symmetry. The membership function describes the degree of symmetry, because in perfect symmetry you have mu, the function mu without the tail. And the membership function, the function as a tail is a continuous function with values ranging from 0 to 1. Okay. So we decide to develop a fuzzy symmetry quantification function to assess the symmetry of the mouth. This idea taking account two main aspects: the numerical aspects of that quantification, and how we can, how can I say, capture the perception of symmetry that the professional dentist can get. Okay. with the quantified symmetry between the two values, we can use that function as a membership function, capture the clinician's perceptions of symmetry, and adapt various scales and magnitudes. Okay, and at the end, of course, we'll talk later on to enhance the predictive modeling for missing data imputations. So this is our function, exponential decay functions, as you can see, that take into account the difference between two contralateral sides and its average, and two parameters, alpha and beta. Alpha is a scale of parameters. For instance, in values in millimeters that you have units without decimal places, you use the alpha equal to 1, which in our case fits very well. To increase the amount of information that you can capture with its formulation, we decided to make beta equal to the Spearman correlation coefficient. In this case, it became not only necessarily a measure of symmetry, but also a similarity measure too. And at the end, we decided for a directional parameter to capture more information about the data. Okay. Sorry. Okay. So we turn off the micro, please. So we developed that concept of directional symmetry when we got the gamma SM function, where gamma is the directional parameter computed this way. And now we decide for imputation. We decide to use the gradient boost machine, as you know well, is a machine learning technique, and consists in the assemblage of multiple learners, random trees, and you know, with the minimization of the loss function and so on. So we use the loss function, the MAA, to approach before, and we decide on the number of trees and so on, and we use that new variable in the modeling of the data. So we can, with the gamma SM function values, the dV1 is the model with the gamma SM, and you can see that you have a R square of 0.967 against the 0.222 without that variable, and so on and so forth. As you can see, this is the error in the V2. There is oh, it's not the error, sorry. And you can see only the only place that you can have some, proximity is the ML2, ML1, as you can see. In terms of variable importance and something, a parameter information that we can get with the GBM models, we see that the gamma SM function have an importance of 69.55 in the DV1, and the V1 you have 61.5.8, and so on and so forth. As you can see, except the ML1 model, we see that the gamma SM variable is perform better. The models perform better than without it. Okay, the last one, you see that is a quite different situation. I think that we don't gave the number of rounds necessary for the GBM to perform a better approximation, but we'll try again with some different approach. And as you can see, the advantage of our function as SM or gamma CM is to improve the accuracy of machine learning models, okay, in this situation. This approach leverages symmetry information between congenital periodontal disease parameters. Benefits of integration. Enhance the prediction, okay, as you saw in the results, the R square, just R square and spread variance are higher there than in the models without this variable. And you can see the models with that variable outperform from far the models without it. The clinical relevance also. And the clinical relevance is assessed by this trial that we did. And we invited 10 dentists, very experienced dentists and periodontists, colleagues of mine in university. They were invited to score the pair in terms of symmetry, the pair of columns, each pair green-blue. And after that, we compute the SM coefficient, symmetry measure coefficient. And as you can see, the results, we found a correlation or a concordance of 0.96 between the score computed by SM function and the same score computed by colleagues. As you can see, that it is a very strong correlation. It means that we succeed to capture the perception of symmetry or quasi-symmetry that the humans can have. So our functions correspond with our intents. To conclude, the statistical methods. There are different methods. I present only one, the more advanced methods, but some authors use also correlation coefficients, Kolmogorov-Smirnov overlapping distribution, distance between the two distributions, the Varadkaya coefficient that quantify the overlapping of two distributions, and so on. We didn't present the results of those approaches here because due to limitations of time. The fuzzy approach, SM function, effectively transform pairs of numerical values into a single value within the 0-1 interval. It means, of course, this because the exponential function is there. This approach addresses the limitations of traditional method of continuous rather binary measures of symmetry. When doing that, we can compute the degree of symmetry between two variables, in this case, located contralateral sites in mouth, and we can see if there is the quantity of symmetry is high or small. To have an idea, in both the median of these values in every site that we compute is 1, okay, and the average are around 0.85 to 0.9. This way those results suggest there is some elevated grade of symmetry between contralateral sites. For further work, we'll intend to validate this measure using different populations and use this symmetry measure in other fields, for instance, like economics, that to access the limit of of the ability of someone to get some credit in terms of his balance between debts and credits already have. Okay,